Now let's go through the solutions to quiz number 9, which covered collisions and linear momentum. So I'm going to start at the first numerical problem here. So it says that two cars collide at an icy intersection and stick together afterwards. The first car has a mass of 1,200 kilograms and is approaching at 8 meters per second due south. So here's our first car. It's heading due south. And we're going to use a coordinate system here, by the way, where positive x is east and positive y is north. The second car has a mass of 850 kilograms and is approaching at 17 meters per second due west. So it says car 2, car 1. So the first question asks us, what is the final momentum in the x direction, that is px prime, of the collided cars? So there's a few things that we need to figure out first before we start doing the plugging in numbers and doing this problem. So first of all, we need to recognize that the external net force in the x direction is equal to 0. So px is conserved, or we can say delta px equals 0. And similarly, for the y direction, if net y is equal to 0, so delta py is equal to 0. So using this conservation, if we need to find px prime, we know that px initial is equal to px prime, or px final. So we just need to find the initial momentum in the x direction. So that's p of the first car plus p of the second car. Now the px, let's put x's there to remember we're talking about x. So px of the first car is going to be 0 because it's only moving in the y direction. Px of the second car is the mass. So that's going to be 850 kilograms times the velocity, which is negative 17 meters per second. So if I plug these numbers into my calculator, 850 times 17, I get negative 14,450 kilogram meters per second. And that is the solution to the first question. So if we continue on to the second question, follows the same logic. We just need to find the y momentum of the first car in this case. And that's just the mass of the first car, 1,200 kilograms, times its speed, which is 8 meters per second. And that's negative because it's moving down in our coordinate system. So I do this multiplication, I get minus 9,600 kilogram meters per second. So that does it for the first two problems, to find p prime x and p prime y. So the next question says, what speed are the stuck together cars moving after the collision? So this part is a little bit trickier. So let's go back to our diagram. We have car 1, car 2. This is the initial picture. And the final picture, the two cars have crashed and they're moving off in some diagonal direction, which we don't know. And we treat them as a single mass here, capital M, by adding the masses of the two cars together, because we're told in the problem that the cars stick together after they collide. So this momentum is not along either our x or our y directions here. So we need to find the total magnitude of this momentum, keeping in mind that it's diagonal and not fully aligned on the x or the y axis. But we already know px, or py prime here, and px prime here. So if we know px prime and py prime, we can use these to get the total momentum. So I can redraw this maybe in a way that makes a bit more familiar to you. This is our p prime vector. This is our py prime, and this is our px prime. So if you haven't realized it yet, we can use Pythagorean theorem to get the magnitude of our p prime vector, since we know px prime and we know py prime. So the magnitude of p prime is equal to the square root of px prime squared plus py prime squared. So this comes out to be, if we plug this in, 17,348 kilogram meters per second. I'm just going to keep all these extra significant figures along for the ride until we find the final answer we're looking for. So this is the magnitude of our final momentum vector, but the question is asking for the speed. So we can convert this to a speed by using p prime is equal to mv prime. Or in this case, it's not little m, but we're representing this as a capital M. So I'm going to change that to capital M. Remember, we're talking about the stuck together cars here. So this is the momentum of the stuck together cars, the mass of the stuck together cars, and the speed, which is what we're trying to find in this problem. So v prime is just equal to p prime over big M, and big M is equal to m1 plus m2. So I can plug in all these numbers. I know p prime from this magnitude here, 17,000. I know m1 and m2 from the problem. So if I plug this in, the number that I get is about 8.46, or round that up to 8.5 meters per second, given the number of significant figures that I have in this problem. So we have one more question left. That's to find the initial kinetic energy of the cars, that is prior to the crash. So the total kinetic energy initially is just our kinetic energy of car 1 plus the kinetic energy of car 2. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Now, because we're dealing with energy here, and energy is a scalar, we don't need to worry about the fact that v1 and v2 are pointing in different directions. We don't really need to worry about their directions at all. We can just take the speed, read it off the problem as given. So I can plug in all these different numbers, something like 1/2 times 1200 times 8 squared plus 1/2 times 850 times 17 squared. And our unit here is joules for this entire expression. And the answer that we come out with is 160,000 joules, if we again round off to our first two significant figures. So that will solve the problem for us. Another interesting question that we can ask is, what is the final kinetic energy of the cars after the crash? So our kinetic energy final, just to go a little bit further, is equal to the kinetic energy of our stuck together cars, which I'll represent with capital M. So that's going to be 1/2 times capital M times V prime squared. Now capital M and V prime we found in the previous question. So 1/2 times 2050 times 8.5 squared. If I plug all of that in, I get about 73,000 joules. So if we compare our initial kinetic energy before the crash to our final kinetic energy after the crash, we do in fact see that energy is lost, which is what we expect for an inelastic collision. And the physical description that we have here fits what we know about inelastic collisions. In fact, it's a perfectly inelastic collision because our two projectiles stick together after the collision.